Okay, so we prove that. So we are going to prove the theorem. Okay, this theorem, real number is uncountable by contradiction. We are going to show this by contradiction. So we are going to prove this by contradiction. So first of all, we do not need to focus on the set of all real numbers, okay? Because there was a corollary. It says that if a set is uncountable, then the superset is also uncountable, right? So we are going to prove this by contradiction, that the real numbers in this set, 0, let's don't have a set of 0 in the real line, 0, 1, is uncountable. Okay, so we are going to prove, we do not look at all the real numbers, but we focus on the real numbers between 0 and 1. And we want to show that just this set of real numbers is already uncountable. If this set is uncountable, then all real numbers must be uncountable. Is that okay? Because it is larger, a superset. Up to this point, if you are okay, could you please raise your hand? Okay, excellent. So we prove this. Okay. So by contradiction, so we assume what? So we assume that the set of real numbers between this line, 0 and 1, is countable. Now, because this is infinite, because there are infinite number of points on 0 and 1, so that means what? If it is countable and infinite, that means that then there exists a 1-1 correspondence, 1-to-1 correspondence between the items in 0, 1 and the integers in n. Is that okay? Okay. So what does it mean? If there is a 1-to-1 correspondence between the real numbers here and in n, so that means what? We can list out the real numbers in this part one by one. We can list out the numbers, the real numbers in this set 0, 1, one by one. So let's say the first one is called R1, the second one is called R2, R3, and so on and so forth. Okay. So we can list them out one by one. So let's say R1, R2, R3, R4, and so on and so forth. Is that okay? We can list them out one by one. So we are going to use that particular 1-to-1 correspondence to list them out one by one. And then we want to show that there is a contradiction. Okay. Now we can list them out one by one. I don't know what the correspondence it is, but let's imagine maybe the correspondence is, okay, let's maybe list the first item as 0.5. Okay. Maybe the second one is 0.142857, 142857, and so on and so forth. Maybe the third one as 0.1333 ... Maybe the fourth one as 0.25, and so on and so forth. 0.25, and so on and so forth. Is that okay? Maybe this is the way that the correspondence is established. So far, if you're okay with this, could you please raise your hand? Okay, now so far so good, right? So we can list everything out. So 0.5, it looks like 0.500. I can give it a lot of 0. 1, 3, 3 is like this, 2, 5, 0, 0, 0. So I can make everyone infinite long, a lot of zeros afterwards. Now, this is the diagonal method. We are going to create a new R. This is a real number R. Okay, this R is simple. How do we create? Look at the first digit. So R is 0 point something. Okay, if the first digit of the first one is just this rule. Okay, it looks at the first digit of the first number, the second digit of the second number, the third digit of the third number, the fourth digit of the fourth number, and so on and so forth. It looks at something like this diagonal. So this is a diagonal, right? It looks at things like this. So it just check, okay, when it is not 1, R will have the corresponding entry 1. If it is 1, then I will make it 2. So I just use 1 and 2. So look at it, this is not 1, so I change it to 2. Is that okay? This is not 1, I change it to 2. This is not 1, I change it to 2. This is not 1, I change it to 2. Is that okay? Is that okay? And so on and so forth. Okay, maybe this is not a good example, so let's make this as 1, okay? Wrong. Sorry. Again. Okay, if it is 1, I change it to 2. If it is not 1, I change it to 1. It's like this, okay? If it is 1, I change it to 2. If it is not 1, I change it to 1. Not 1, change it to 1. Not 1, change it to 1. So I will have R defined. Is that okay? Is that okay? Is that okay? So what is so special about this R? So first of all, R must be a number that is inside this range, 0.1 and 0 and 1. So it is a number that is between 0 and 1, and R is not equal to R1. Why? Because the first digit of R is not the same as the first digit of R1. R is not equal to R2. Because the second digit of R is not equal to the second digit of R2. Is that okay? R is not equal to R3 because the third digit of R is not equal to the third digit of R3. So R cannot be listed. R is not any number Rk because the kth digit is different. Is that okay? Okay, so we get a contradiction. The contradiction comes from what? The contradiction says, here there is a 1-to-1 correspondence between any real number to n. But here we find that for a certain number, there is no correspondence. So the contradiction comes from there is a correspondence and there is not a correspondence. So we get a contradiction. So what does it mean? It means what? It means the first assumption here has to be wrong. So if this is wrong, 0, 1 is uncountable, and 0, 1 is uncountable, then the real numbers must be uncountable. Is that okay? Is that okay? Good. Good. Now there's something interesting. So 1-1 correspondence is not limited to, as I mentioned, it is not limited to a set with the n. Okay. So you can establish 1-1 correspondence between two sets, any two sets. And then if they have a 1-to-1 correspondence, you can say that they have the same size. Okay? So imagine you have this square. This is a square. This is a square. This square is 0, 1, 1. So this is you can think of this as 0, 0. This is 0, 1. This is 1, 0. And this is 1, 1. Okay? Okay? So you can take out a point here. Any point here. Any point here you can represent as it is a point x and y such that x, y, they are both in 0, 1. Okay? So this point is a coordinate point with x coordinate x, y coordinate y. And then you can talk about a set like this. This set represents what? This set represents all the points within this region. So this is this set. Okay? So you can think of this as a set of infinite number of points. Okay? Okay? And interestingly, this will have one-to-one correspondence. So there is a one-to-one correspondence of this set with the real number set 0, 1. Okay, how? This is easy. Okay. You have, for instance, you have a point x. Maybe x is equal to 0.5231465, blah, blah, blah. And maybe you have a point y. Y is equal to 0.01020304, whatever, blah, blah, blah. Okay? Now, I can make these two corresponds to a point z as follows. I take the first digit of x, and then I take the first digit of y. I take the second digit of x, I take the second digit of y, I take the third digit of x, I take the third digit of y, and so on and so forth. So it is like this one goes to this one, goes to this one. Is that okay? Is that okay? So you can see that, okay, if I have any two-dimensional point x, y in this region, after this transformation, I get to a real number between 0 and 1. Is that okay? And similarly, if I have a number between 0 and 1, I can break it down into two parts, and then it becomes a point in this one. Maybe the 0, I should be more careful. So let's have this 0 like this. Okay. Yeah, this removes some of the problem. Okay. Okay. So in that sense, for any point that is on the line 0, 1, it corresponds to a point in the two-dimensional space. So it is quite strange. Okay. So the number of points on the line is equal to the number of the points in an area. Okay, quite different, quite amazing. But if you believe what we have talked about today, you are already amazed that, okay, you have the same number of integers you have the same number of even numbers as the same number of natural numbers. Or you have the same number of even numbers as the rational numbers, right? Yeah, this is something that is confusing, but also amazing, and I believe it is also true. Okay. So this is the end of the discussion of countable and uncountable set. Okay, just last minute. Okay, so we have a minor theorem, unrelated thing that we want to talk about. This is the inclusion-exclusion principle. So we want to show that so assume that all these sets, okay, so we get back to our daily life. All the sets here are finite. They are finite sets. And this time we want to count what is the total size, okay, of A1 union A2 union A3 up to AK. And then we want to show that it is equal to what? It is equal to A1 plus A2 plus ... plus AK. And then minus the union of the intersection of any two sets, A1 intersect A2, A1 intersect A3. This is AK minus 1 intersect AK. So this is any two sets. And then we need to add back the intersection of any three sets, A1 intersect A2 intersect A3. AK minus 1 minus 2 intersect AK minus 1 intersect AK. So this is any three sets. And so on and so forth. So for any 4 sets, then we need to deduct. For any 5 sets, the intersection, the size, we need to add back, and so on and so forth. So in the end, so it needs to add. In the end, it will be minus 1 to the power k minus 1, the intersection of all sets. The intersection of all sets. Okay, so this is called the principle of inclusion and exclusion. Is that okay? Okay? And then we want to prove it. So how do we prove? The proof is simple. Okay? Is it? Let me see. Okay, so how do we prove it? So the idea is like we look at all the items. So this represents a set. So A1, union A2, union A3, union A4, and so on and so forth. This represents a set here. So it may be irregular in shape. So let's say this set represents A1, union A2, union A3, union AK. I have a certain element here. Now for each element here, it is inside this set, right? So it should be counted as 1 in this side. So to get the size of this set, we look at every element in this set and count it as 1. Is that okay? So this is the natural way to get the size of a set. So a set contains orange, apple, banana. Okay, so you look at apple, okay. You see apple, so you count it as 1. You see orange, you count it as 1. You see banana, you count it as 1. So together, you have the total count equal to 3. So the size is equal to 3. Is that okay? So for each item, it should be counted once on the left-hand side. Is that okay? What we are going to show is that for the same item, so let's say for this item X, it will also be counted exactly once on the right-hand side. If this is true, then we are done. Is that okay? Okay? Okay, how is X counted? Okay, so we assume that, okay, so X is inside this part, but it can be inside A1, or it can be inside A2, or it can be inside A3, or it can be inside A2 and A3 together. Is that okay? So assume that X is inside. I don't know how many sets, T sets here, where T is at least 1, but at most K. Is that okay? So we assume that, so with different kinds of X, we are going to count it differently. So for X here, in this set, A1 union A2 up to AK, it may be inside just one of the sets, or it may be inside 2 sets, or it may be inside 3 sets. But the largest number of sets will be K. Is that okay? Okay? So it is inside T sets. Okay, T sets. So if it is inside T sets, then what will the contribution of this X will be? So in T of the sets, X will give a count of 1 because it is inside that set. And in the remaining set, it will give a count of 0. Is that okay? Is that okay? Is that okay? So you will have what? So some of them will be, X will be contributing 1 here. Some of them X will be contributing 0 here. But the total contribution here will be T. Is that okay? Is that okay? Yeah, some of the set 1, some of the set 0. T of the set, it will contribute 1. The other set, K minus T set, it will contribute 0. So the total contribution is T. If you are okay with this, could you please raise your hand? Okay, good. The next one, how about this one? X is inside exactly t sets. So if it is inside A1 and A2, it will contribute 1. If it is inside A1 but not A3, it will contribute 0. Is that okay? So some of them will be 1, some of them will be 0 here, the contribution. So how many of them will be 1? It must be, this one is from the t sets that X it is, and this one is also from the t sets that X belongs to. So how many cases are there? There are going to be t choose 2. Is that okay? So the contribution here will be t choose 2. Is that okay? And then it is a minus. Okay? And then it will have plus t choose 3, the contribution here, minus t choose 4, and so on and so forth. And in the end, this one, so if it's about all the k sets, if t is not as large as k, then it will become 0 already. So the largest possible cases, it is when you are considering t sets, exactly t sets. So it is minus or plus minus 1 to the power t minus 1, t choose t. Is that okay? So this is what we have. So one is plus, the other one is minus, and then plus, and then minus, and then plus, and minus, and so on and so forth. Depending on the value of this one, if it is odd, then it is plus. If it is even, then it is minus. So when it is t, then it is minus 1 to the power t minus 1. Is that okay? And then this adds up to 1. Okay. Just compare this with what? Just compare this with the binomial extension of 1 minus x to the power t minus a. Yeah, compare this with this one. Yeah, I'm overrunning. So why is it 1? It is because 1 minus t plus this one minus this one plus this one minus this one, and so on and so forth, it is equal to 1 minus 1 to the power t, and it is equal to 0. So 1 is equal to this one. So go home and check. Okay, so this is not that difficult. You can easily check that this one is equal to 1 by using the binomial theorem. Okay, that's it. Okay, sorry for overrunning.